This is part two of the chapter four of video solutions. For factoring, you always want to check if you can pull out a GCF, a greatest common factor. I can pull out both a y and a 2 because these numbers are both even and because they both have at least one y variable in there. So when you're factoring, you're kind of dividing each factor by that, but I kind of write it on the outside. So when I pull the 2y out, I get a y minus 4. And you always want to ask yourself, can I factor this further? And since y minus 4 can't be factored further, you can. For this one, again, I want to check, can I pull out a GCF? I see the 2 3s. I was like, oh, maybe I can pull out a 3, but 8 is not divisible by 3. But since the 3s are prime numbers, it actually makes this really easy to factor. So the only way to get 3x squared is 3x times x. The only way to get a 3 is to do 1 times 3. And so I'm kind of right in both cases. I know I have to have opposite signs. I can either have a 3 or a 1. And I'm not sure where the 3 goes and where the 1 goes, though. So I'm going to try, and I'm actually intentionally doing the wrong answer first, just to show you how to check your answer. So if I try to put the 3 next to the 3 and the 1 next to just the x, I want an 8x. But if I put them in this position, I get 0x. So that's not going to work out. So I'm going to try instead to swap the numbers. I'm going to put 3x plus 1, and I'm going to put x minus 3. And let's see if that works. So I kind of check the x terms. I almost get what I want. I get a minus 8x, but I don't want a minus 8x. I want a plus 8x. So the number's right. The signs are wrong, so I just switch the signs. And you can check that they work out here. So just try the different possibilities. There's one little tip you can do. In addition to just factoring, let's say you get stuck. You can actually use, even though we use the quadratic formula to solve a quadratic equation, we can use it to actually factor it as well. I'm going to kind of do a backwards approach. So I'm going to assume this was a quadratic equation. It was set equal to 0. I'm going to find the solutions or the x-intercepts or the zeros or roots, whatever you want to call them, to the quadratic equation. And here's what I get. So if one of my solutions is negative 3, that matches up with the factor of x plus 3. So if I know one of my solutions is negative 3, that means x plus 3 is a factor. And then I can use that to more easily find out the other possibilities. I can see that 3x and the 1 work out here. So you can kind of use quadratic formula to kind of reverse engineer your solutions. A little harder to spot is that the point 3 repeating is the 1/3 solution, but it does lead to that factor I use with the blue arrow there. Number 13, again, you want to check if you can factor out a GCF. I can't in this case, so I'm going to just do all the possibilities. Well, what's the possibilities to get a 9w squared? What's the possibilities to get a 25 at the end? In the middle term, I don't worry about so much, but I'm going to choose the most convenient way to factor a 9. 3 times 3, 25. I'm going to do 5 times 5, and this just happens to be a perfect square binomial. So that attempt works on how to factor it, but instead of writing the 3w minus 5 twice, it's nicer to write it as just 3w minus 5 squared. You can still use the quadratic formula to sort of reverse engineer it. It might be hard to spot it, but if I use quadratic formula, you notice you get the same solution twice, so that kind of shows you, oh, it's going to be a perfect square binomial. And that's how when you convert to a fraction, you get 5 over 3, so that's how that works. For this one, I'm going to try solving these quadratic equations 3 different ways. If you like factoring, that can work. So you can factor this. It's actually a difference of perfect squares. Your solutions are going to be positive 5 and negative 5. Again, you factor, and then you set each factor equal to 0. If you like using the graph method of doing it, so graphing that parabola in your calculator, and then using the option of second calc 0, you can see it actually hits perfectly those numbers negative 5 and 5. But to make sure that you're sure that it hits those x-intercepts, so you're going to use second calc 0. Wait. So and you left bound it, right bound it, hit enter, and then it finds the solution exactly. Notice how the y is equal to 0 there. If you want to find the other 0, which is on the right side in this case, you just do that again, and both of those zeros in 2 different cases. This is kind of time consuming, so I don't love it. But one that's really fast is quadratic formula. You can sing the song if you want, but if you have the program in your calculator, you don't even have to write down. You don't even have to use the do the calculations yourself. What I would like is if you use this on a test, I want you to write the formula and I want you to like plug in the numbers, but not actually do the calculation. So I'd advise you use the quadratic equation program, but just write down like the formula with the numbers plugged in. For number 15, I'm going to do the same thing. I'm going to try to factor it. And I'll only make one attempt. That should be minus 1x right there, but altogether it makes a minus 4x. But factoring is impossible in this case. At least trying to factor it using integers. It just doesn't work out. I can graph it, and when I graph it, it's not going to be as pretty as the other one. But I noticed that when I go to graph it, it doesn't have any x-intercepts at all. So this has no real solutions. So the only way to actually get your solutions, since your solutions are imaginary, is to use quadratic formula. So what's going to happen, you'll notice that that discriminant, the part that's underneath the radical, is going to be negative. So all your solutions are going to be imaginary. So I can run that into quadratic formula, and I get 1 plus 1.41i and 1 minus 1.41i. If you happen to know that 1.41 and some change is square root of 2, you can just you can write that. But notice how if I do it by hand, I'm going to calculate that discriminant part in my calculator, but I'm not going to use the square root symbol. I'm just going to calculate what that is. That comes out to a negative 8. Negative 8, I am going to square root it, but I'm going to square root it and simplify it by hand. So I have 2 plus the square root of negative 8 all over 2. I'm going to simplify that radical. Square root of negative 8 is just square root of negative 1 times the square root of 8. You can reduce the radical. That's 2 times the square root of 2 by prime factoring it and pulling out the pairs of 2's. And then I can divide everything by 2. So you get 2 divided by 2 is 1. And then this thing, the 2's cancel out. So you just get I times square root of 2. So that's where I get 1 plus square root of 2i and then 1 minus square root of 2i. That solution there. Again, you could have, if you happen to recognize 1.41 as square root of 2, you can work it that way too. But doing this by hand or using the quadratic formula program in your calculator or just entering it manually in your calculator are both valid ways of doing it. Whereas factoring doesn't work here. Quadratic formula will always work to find the solutions. Great formula. Number 16, I'm going to actually just lead with quadratic formula, but I can't. To use quadratic formula, you have to have your equation in standard form. Well, that 6 has to be like hanging out with everybody else. You have to have, a quadratic expression equal to 0, and to move the 6 over, you just add 6 on both sides. I can try to factor it, but I'm pretty sure this can't be factored. So before I even try to factor it, I'm going to try graphing it or using quadratic formula first. I at least see that it'll have solutions. It'll have 2 real solutions because it has 2 x-intercepts. So I can calculate that using the x and y intercepts. And so using the second calc 0 option, and I can left bound it, right bound it, hit enter. Again, that's kind of time consuming, but notice what values I get. 0.837-ish and 7.16-ish. And notice the y value there, it doesn't look like 0, but it actually is. It's basically 0. It's a really tiny number because it's a number in scientific notation. But if I use the quadratic formula program, and again, I'm putting 6 as C, not negative 6, because you have to have it in standard form. I move that 6 over. Very important that you do that. But when you do that, you'll get those same x values that you got by graphing. Quadratic formula, great way to solve any quadratic equation. Numbers 17 and 18, don't worry about that. Those are not in the test. Neither are 19 and 20. But these are basically just graphing problems, and you're like finding the intersections, but they are not on the Chapter 4 test. I'll make a separate video for people who have inquiring minds and want to learn how to do that, but we'll maybe spend a little bit of time looking at those solutions, but not for this test. For 21 through 23, if you remember on a little Gizmo or Explore Learning document, we went and there are questions about the discriminant and what kind of solutions you have when your discriminant is positive, negative, or 0. So we're going to find the value of the discriminant. That's the b squared minus 4ac. So I'm going to calculate that for each of these equations, which are conveniently already in standard form. The first discriminant is 64. I don't really care about the number it is. I care about whether it's positive or negative or 0. This one's positive, and whenever your discriminant is positive, you'll have two real solutions. Now, what if you didn't memorize that? Well, good news. You can just graph the equation and confirm that it has two real solutions. So even if you don't know how to calculate the discriminant, you can maybe reverse engineer it and go, oh, wait, I have two real solutions, so this discriminant must be positive. For 22, again, the discriminant is using that b squared minus 4ac. And this time when I calculate it, I'm going to get a negative number. I don't really care that it's a negative 35. I just care that it is negative. When you get a negative discriminant, what it means is that you have two imaginary solutions. So every polynomial of degree 2 has roots, but sometimes the roots are just not real. Like they're not, they're going to be imaginary instead. Again, you can just confirm by graphing whether it has positive or negative solutions. You can use quadratic formula as well to confirm it. You'll notice because you see how there's like a plus after the like 1.6 repeating term. That 0.98 would have an I after it. I just kind of ran out of room on the calculator. But the fact that there's a plus and a minus after that implies that it's written in the form of a plus bi. I kind of prefer instead to just look at the graph. I think that's a better way of confirming that it has no real solutions. It has no real x-intercepts. That parabola is never going to hit the x-axis. 23, same thing. I want to find the value of the discriminant, use it to figure out if I have any real solutions to the equation, any real x-intercepts. If I do the negative b squared minus 4ac, all I care is that the discriminant is positive. A positive discriminant means I have solutions, and that there's going to be two real solutions to that quadratic equation. If you forget, once more, like, man, I want to know how many solutions I have, but I don't, I'm not comfortable with the discriminant, well, you can just graph it, and you'll notice that, boom, there's two x-intercepts, two real solutions to that equation. You can find them if you want, but we just want to know how many there are. For 24, we're relating graphing a number on a complex plane to graphing on a coordinate plane. On a complex plane, there's a real and an imaginary axis. Now, on the way that corresponds or kind of relates similarly to a coordinate plane is that you have an x and a y-axis. The difference is that x and y-axis, they're both real numbers. It's just two-dimensional. A complex number is not exactly two-dimensional in that way because the I part is imaginary, so it's a complex number. For 25, we're trying to sketch a graph of a function that has no real zeros. Well, we just talked about this in number 22. So if you look at 22, if you just sketch any quadratic equation that does not have two x-intercepts or any x-intercepts at all, really, because it is possible for it to have one x-intercept if it just bounces off the x-axis, but all of these are sketches of parabolas that have no real solutions. Number 26, this is probably the most practical one. You'll use this in physics class. That equation of the height of the object is given. That negative 4.9, by the way, comes from gravity. Gravity in meters per second squared is 9.8, and we take half of the gravity for reasons that you find out when you take calculus. That 68, even though it's not explicitly said in the problem, is the initial velocity. It's what the initial velocity of that rocket is. And I want you to do one more thing in addition to finding the max height and when it hits that max height. I want you to figure out when it hits the ground. Now, the initial height of this rocket is launched from the ground. So I don't need to write that plus 0, but if you ever see a different number besides plus 0, it means it's been launched from, like, say, a platform or something. But your max height is going to occur at your vertex. The y-coordinate of that vertex is going to be what the max height or max altitude is. The x-coordinate of your vertex, like the h, is going to be when it hits that max height. So the k is going to be your altitude. The h is going to be the time at which you hit that altitude. You can use negative b over 2a to figure out your vertex. So I'm going to use that strategy there. So I get about 6.94. And remember, that's the x-coordinate or the t-coordinate if you want to think of it that way. So that's the time in seconds that you reach the max altitude. Well, how do I figure what my max altitude is? Well, that's the k or that's the y coordinate of my vertex. So down here, I'm going to take that time value of 6.94-ish, around to, I can put more decimal places than I need to. I can just put 6.939 just to be really safe. I hate to use a rounded value and another rounded value. You can also store the value in your calculator, but that's being more careful than you need to. But if I evaluate this in my calculator, I get about 235.9 meters. That's going to be in meters, not in feet. So my max altitude will be about 235.9 feet. I want to find out when it hits the ground. Well, it hits the ground when your height is 0. I can solve for that by hand. So all of these so far, other than running the calculations in my calculator to simplify stuff, I've done everything pretty much by hand so far. And so I can solve, find the roots. I can factor this thing to make it a little easier and solve for when the height is equal to 0. But the decimal part, the calculator part, I'm gonna, at the actual like little division and addition, I'm gonna run that in the calculator again. Notice how that time is actually twice as long as it takes to reach its max height, that's always gonna happen when your object is launched from the ground. Now, if you don't like doing this with the negative b over 2a formula or with factoring, I'm going to show you option 2. Option 2, we can find the max height. We can find when it hits the max height. We can find when it hits the ground by graphing. So what I'm going to do is I'm going to put that equation, and I choose to put it with the in descending order. I like to put the x squared part first. I know it was t squared, but your calculator takes x squared. I'm going to zoom fit so I can see the graph better because I didn't like how I was seeing the graph. And I can kind of see the parabola, but I'm going to use the trace key, kind of bump over to the side. I'm going to hit enter and it recenters that graph. And there we go. I like the way that looks. I can see the parabola. I can see where it starts, stops. I can see the max altitude. I can see the x-intercept. And I can use second calc maximum to get the vertex. Now, it's the maximum because this is a concave down parabola. And again, the x value is like the t value, that's in seconds. The y value is the max altitude, that's in meters. If I want to find the 0, which is where it hits the ground, I use second calc 0, left bound, right bound, hit enter, and that gives me the 0, or where it hits when it hits the ground. And then notice how it has a height of 0, the y is 0, the x is 13.87 seconds and some change. But that's how I find that graphically. So you can use either option, but I care that you know how to find those two things. Number 27 is not on the test, so you don't have to worry about that. So if you can do these on here, you'll be in good shape. Good luck.